So today, continuing our discussion of series for the rest of this chapter, right? We're going to take a look today at the integral test and the P-series test. So the integral test and the P-series test are not going to give us ways that find the summation values when they converge. They're just going to tell us whether or not they converge. So we've entered those gray areas that I warned you were here. So to start with, we have the integral test. So like I said, generally speaking, we're not going to be able to find the actual sum most of the time. So here are two ways that we're going to do this. The first one is the integral test. If f is positive, continuous, and decreasing, and we do have to check that before we start, positive, continuous, and decreasing, and a sub n is equal to f of n, then the summation from n equal 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. So this is telling us that we have the ability to find out if it converges by finding an integration of a related function. And if it has a value, it's not infinite, then our value, our sequence, our series will also have a value. It doesn't say that those values are equal though, right? They're not equal. It just tells you that they both converge or both diverge. All right, so we're going to do an example. We have a very fun one, right? Looks like we're going to need some advanced integration technique for this, right? That's not just a standard one. What is it? It's a U sub. We're going to use U substitution for this, right? So generally, when we're looking for ones that integral test applies to, it's something that you know how to take an integral of without it being something crazy and awful. Okay, so we're not looking at something that's stuff from Calc 2 where we had lots of integration technique stuff. That's typically not the way it goes. It's usually something that you can identify pretty quickly. I know how to take the integral of that. And since I know how to take the integral of that, the integral test is a good one to use. Does that make sense? Okay, so we're going to take this equation, or this sequence, this series, and we're going to find the related function. So we're going to, consider the function f of x equals 2 over x ln x. This is a related function, right? Okay. So we have to check and make sure that this function meets the criterion. If you flip over here, we'll remind ourselves it needs to be positive, it needs to be continuous, and it needs to be decreasing. Okay, those are our three tests. Now, we don't have to write out lots of detailed information like when we were looking at the bounded and the monotonic stuff. That's not the goal. But we need to check and make sure it actually fits that criterion before we move forward, okay? So as we take a look at this, is this positive? Yes. Yeah, it's positive, right? Think about graphs of log, right? Log graphs are always positive. At least they are when we have values that are bigger, or 1 or bigger than 1, right? And we also have the x value itself. So if x is positive, because it would be, because we're dealing with n, right? It says n goes from 2 to infinity. K, in our case, k goes from 2 to infinity. So as long as k is bigger than 2, the log is going to be bigger than that, right? It's going to be positive. And the k value itself is going to be positive. So we're going to get a positive value. So this is positive. That checks out when x is greater than 1, right? As long as x is greater than, not greater than, equal to greater than 1, it works. And our k is, in fact, I'll actually write down that it is, or our k is in fact greater than or equal to 2, right? Starts at 2 and goes up. So that one works. The second one is continuous. Is it continuous?
Yes.
Yes, right? At least it is when x is bigger than what? Think about this function. Where would it have a discontinuity? Or where would the continuity start? You could say it that way.
0.
Yeah, as long as we're bigger than 0, right? Log is not defined for values that are negative. So as long as we're bigger than 0, we're good. And our k values are, in fact, bigger than 0. They start at 2. So this is continuous when x is greater than 0. And again, our k is bigger than 2, so that satisfies it. That works. And then the last one is decreasing. Is this decreasing? Yeah, it is. How do you know? The log function does what?
Decreases.
Well, it's increasing. The log function itself is increasing. What about x? Also increasing. So that means the denominator as a whole is going to continue to increase, which makes the fraction decrease, right? The denominator is increasing, so my fraction's decreasing. So this is decreasing because as x goes to infinity, ln x also goes to infinity. So my 2 over x ln x will go to 0, right? The values themselves. I'm trying to cram a lot into this screen today. Is it still readable at the size it is? We're okay? All right. So since we have all those details, the integral test can be applied. Right, we have to check the conditions at the beginning to make sure we're working with something that's actually fitting in that criteria, right? The hypotheses have to be satisfied. Yeah.
So is that going to be on every one of these that we might want to use it?
Yep, anytime you
Or
use
is
it, you have to check those things. So just a little tidbit of justification is enough. It's not going to be a full blown out like we were doing with the bounded monotonic. Those we had a lot more that we were doing, right? But just a justification as to why that's happening.
Did you want us to show that there was continuous?
Just a verbal justification, like what I've written down right now is enough.
Okay.
Okay, so this is all based on what you know from algebra, right? What you know about functions, right? This is because it goes back into functions that we're showing this for. So for these functions, it's the function itself. Is it continuous? Is it decreasing? And then the other one was what? Oh, is it positive, right? So it's what you know about functions that proves these things. Okay. Okay. So now we're able to use the integral test. So I'm going to take all of this and move it actually over to the other side of my screen. So we can consider now the integral from 2 to infinity of that function that we created, 2 over x ln x dx. And who was it said u substitution? Robert, you said it was going to be u substitution, and you're right. So if this is u substitution, what's u? Ln x. And du is 1 over x dx, right? Okay. So we can make a substitution. We'll leave off our limits of integration for now. So let me come down here. This will be the integral of what? Two over u du. It says 1 over x dx. Sorry, Noah. It's because I'm writing so tiny over there. It's kind of hard to read it. Make it a little bit bigger. 1 over x dx. Okay. What's the antiderivative of 2 over u? Yeah, 2 natural log, and it's natural log of the absolute value of u, but our u values are already positive, so if you want to leave off the absolute value here, you could do that. But we don't really have u. Our u is actually equal to natural log of x. So this is really 2 natural log of the natural log of x. Agreed? Okay. But our limits of integration actually go from 2 to infinity, and if you'll remember, you can't put an infinity over there, right? These are evaluation bars. I can't evaluate at infinity. So the way that I do that, give myself a little bit of a space, is that I use a limit at the beginning, and I'll choose another letter. I'm going to choose b. So b goes to infinity, and then the upper limit of integration would be b. Okay? It's Calc 1 stuff, but it's been a while, I imagine. Right? Okay, so we're going to evaluate b to infinity, the limit of 2 natural log of the natural log of b minus 2 natural log of the natural log of 2. Okay. 2 times the natural log of the natural log of 2. What is this, generally speaking?
A number.
It's a number. This is a number. We don't even care. Remember, we really don't care what these things are, numerically speaking. We just need to know if it's a number or if it's infinity. But the first piece, where I've got the limit as b goes to infinity of the natural log, 2 times the natural log of the natural log of b, what is this? That's infinity, right? This natural log of b inside is infinite. And I've got another natural log of something that is infinite. And then times 2. That's infinity. So this is, at the beginning, is infinity. And infinity minus a number is still infinity. So this is infinite, right? This antiderivative is an infinite value. What's that mean?
Divergent.
It means it diverges. And since... Okay, so I'm going to come back over here where I've got a little bit more space one more time. Sorry to go back and forth on my screen. So the integral from 2 to infinity of 2 over x ln x dx diverges. Thus, the series from k equal 2 to infinity of 1 over k ln k also diverges. And I said it before, but I'll reiterate this again. This is by the integral test. As long as it's on there somewhere, we put it at the beginning as well, then we're good. But it is the integral test that's telling us that, yeah.
So if we get a number for the
Yeah.
integral test, that just means it converges. That's not
Correct.
saying that that's the sum.
Exactly. So if at the end of this over here, we had gotten something like, 52 or whatever, right? It's a number. That tells you it converges. And then the integral test then would tell you that your series converges as well, but not that it converges to the same 52, just that it converges.
Okay.
Yes, very good point.
This
Yep.
question doesn't really matter for the question,
Mhm.
but on continuity, x is greater than 0, what about at 1? Is it continuous at 1?
Well, it doesn't matter on this one because it started at 2,
Yes.
right? At 1, it wouldn't work either because the natural log itself would be 0 and you get a 0 in the denominator.
Okay, so it's continuous when x is greater than 1, technically?
Did I write something down funny? Is that what you're telling me?
Well, you just put x is greater
Oh,
than 0.
yeah, you're right. I did
Okay.
write down 0 there.
I
and
wasn't
meant to
sure
put
if I
1.
wasn't remembering how to
Nope,
do
you're
continuity.
correct. That should be greater than 1. My apologies, yeah. Yeah, no zeros in denominator and natural log of 1 would give us a 0. Very good point. Okay. Anything else? Okay, so it becomes a Calc 2 question really, right? Because we used the integrals and we did a lot of integration in Calc 2. Okay, second test. Actually, sorry, one thing before our second test. This is a specific case of the next test, but the harmonic series. Harmonic series is one that's very counterintuitive. So consider the series summation from k equal 1 to infinity of 1 over k. Notice the limit is 0 of the sequence, right? The sequence 1 over k's limit is 0. So you're probably inclined to think that the series would converge, or at the very least, we're not able to use a divergence test and say we know it diverges, right? The divergence test we talked about last time. If the limit goes to 0, it may converge. So we're going to look at this further. If you have the summation from k equal 1 to infinity of 1 over k, you'd have 1 over 1 plus 1 over 2 plus 1 over 3 plus, dot, 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 and this should continue on like this way, right? On forever. S sub n would correspond to this area of the rectangles, and each rectangle lies above the equation y equal 1 over x. So S sub n is greater than or equal to the area under the curve because it's rectangles that are above the curve. We can draw a picture if you want. Do you want a picture? I don't have a lot of space on the screen. I'll do it up here. It'll be a tiny picture. So if we put our picture like this, every rectangle I draw, no matter how tiny it is, and I'll draw a bigger one just because otherwise it's hard to draw. No matter what the height is that we use, we're going to be tending, hang on how they do it. Oh, because our value is coming from the left, it's going to be drawing rectangles that look like this. The rectangle heights are all going to be above the curve. And the equation 1 over x itself, if we think about it as the integral test, gives you the natural log. Right, we got natural log in the last question we did. And when we look at convergence of natural logs, they don't converge, right? They're infinite. So I'm just saying this in shorter terms. So the area under the curve is the integral is greater than or equal to the area, the integral from a to n plus 1 of 1 over x dx, which equals the natural log of n plus 1. As n goes to infinity, this natural log itself will have a limit that's an infinite. So my partial sums, s sub n, is greater than or equal to infinity. Hence, the summation from k equal 1 to infinity of 1 over k diverges, even though the limit of k to infinity of 1 over k is 0. Okay. This is counterintuitive. The sequence goes to 0, right? It does. The sequence of 1 over k goes to 0. The graph looks something like the one up there, right? That's the graph of it. It goes to 0, no question. But the area under that curve is infinite. And you did the area under that curve and found that fact in Calc 2. We may have even done it, actually, I think it was Calc 1 where we first see that one. Yeah, it was Calc 1 because we have 1 over x. And, do we do that one in Calc 1? I think we do. I think we do it in Calc 1, at the very end of Calc 1. Regardless, you've seen it in one of the two calculuses, right? And we have something that's infinite as an area under the curve. And so, again, by the integral test, we could even say, since the integral of 1 over x dx is infinite, the series is also going to be infinite. So it's not enough to say that that divergence test has the converse and the inverse true, right? The original statement and the contrapositive we looked at last time were true, but the converse and the inverse are not. So in particular, you might want to sort of think about, well, what other things that look kind of like 1 over k or 1 over x would be divergent as well? Right? What else does this apply to? And that's what leads us to the P-series test. So if we have, if you have the summation from k equal 1 to infinity of 1 over k and it diverges, which it does, would the summation from k equal 1 to infinity of 1 over k squared diverge? Because those are very similar graphs, aren't they? If you look at the graph of 1 over k squared, it looks a lot like 1 over k, 1 over x squared. The P-series test actually tells us exactly when something of that form converges and when it doesn't. And that's actually really nice too. There are some tests that just tell us when something converges, and then they say things like, it's inconclusive in other situations. This one's not like that. It's either converge or diverge, just like the integral test. It's one or the other, black and white. So the P-series says that if the summation from n equal 1 to infinity of 1 over n, if you have that, 1 over n to the p, it converges if p is greater than 1, and it diverges. I feel like I've got an equal sign missing somewhere. Let me figure out where it is. It's on this one. It diverges if 0 is less than p is less than or equal to 1. Okay, we had the equal to 1 case just a moment ago. It diverged. If p is 1, we've got the sequence 1 over n. That diverged. Okay? This one's really easy to use. You want to see? Integral tests was a lot of work to use, agreed? Like it was all previous knowledge kind of stuff, but it's pretty easy, pretty bulky to use, a lot of work to it. This one's really easy to use. So we're trying to decide if it converges or diverges. Is it of the form 1 over n to the p? Yeah, it's the right form. It's 1 over n to the 1/2. So that's the right form of 4 over n to the 1/2, 4 over k to the 1/2. It's the right form. So all we have to do is to look at the exponent of the denominator. And we have to consider whether it's bigger than 1 or less than or equal to 1. Which one is it? It's less than 1, right? So the p-value, which is 1/2, is less than 1. So what did the P-series test say is going to happen? It diverges. So the summation from k equal, this one is 6 to infinity, of 4 over k to the 1/2 diverges. Why? By the P-series test. Please, please, please get in the habit of telling me what test you're using. Don't make me guess. I want to know what test you're using and that you know what test you're using. So state it.
You say the theorem instead, is that okay?
If you want to, and you say theorem 910, that's fine. Yeah. You're probably not going to remember theorem 910 when it comes to your test, but you might remember the name of it being the P-series test. So that's what I usually default to. Yeah. Any questions? Do you like that test?
Yeah.
I like that test a lot. That's one of my favorites. Yeah. Okay. So that's what we're going to be doing homework for today.